Hi everyone, welcome to lesson 1.12, Principles of Neutralization Titration. This is adapted from the PSHS Chemistry 4 module lesson 1.12. For this lesson, we have the following targets. First, to apply the concepts of titrametric analysis to a wide variety of problems in analysis. Second, to choose the appropriate classical method of analysis needed for specific problems. In the previous lesson, we have learned important terms used in titrimetry and some basic calculations in titrations. In this lesson, we will look into the types of titrations, titration curves, acid-base titrations, particularly strong acid, strong base titrations, and applications of titrimetric techniques. Here we have the general types of titrations. First, we will look into the gravimetric titrations. In gravimetric titrations, the titrant dispensed to the analyte is weighed. It's a complex setup, therefore the volumetric counterpart is preferred by analysts. However, this technique offers speed, convenience, elimination of temperature corrections, greater precision and accuracy in measurements, and are easily automated. Here's an illustration of a gravimetric titration setup. Instead of a burette, we have a reagent dispenser, and the weight difference between the weight difference before titration and after titration is determined by weighing. Next, redox titrations. This is a technique involving a reaction between a reducing and oxidation and an oxidizing agent. It should be balanced accordingly considering the transfer of electrons, and the endpoint of the titration is signaled usually by color changes or potentiometric changes in the reaction mixture. So this titration may be carried out by visual inspection of the endpoint, or it may be carried out by potentiometric changes using a probe, which will tell us when the equivalence point happens. Next, complexation titrations are titrations involving the reaction of a metal ion with a suitable ligand to form a complex, and the endpoint is signaled by the indicator or by an instrument response. Again, we can have visual inspection of a color change or an instrument response. So here is an example of a complexation titration involving EDTA. So before the equivalence point, the mixture color is red due to the magnesium ion indicator complex. At equivalence point, it's purple, and beyond equivalence point, it's color blue due to the presence of the uncomplexed indicator. Next, precipitation reactions involve the reaction of the titrant and the analyte forming a partially soluble precipitate. When we say that the precipitate is partially soluble, we usually take it to mean that, well, in all practical sense, it's insoluble. And the endpoint is the formation of a precipitate in the reaction mixture. An example is argentometric titration with silver nitrate. Here's an example of precipitation titration where before the equivalence point, a precipitate is formed, but at the end point, the formation of a red precipitate marks the end of the titration. Next, acid-base titrations. This is a titration technique involving the reaction of an acid and a base. There are different variations which involve differences in the strengths of the acid or base in the titration system. So here's a typical strong acid, strong base titration using phenolphthalein. Before equivalence point, the analyte mixture is acidic. Then at equivalence point, the mixture should be faint pink. And if the pink color is too intense, that means this is already beyond the equivalence point or the endpoint. Also, here's a system using methyl red as an indicator, red in acidic solutions, orange at equivalence point, and yellow signifying a basic mixture. Moving on to titration curves. Titration curves are plots of the analyte concentration in the y-axis versus volume of the titrant added in the x-axis. So there are two types, a sigmoidal curve looking like this and a linear segment curve looking like this. We are most familiar of the sigmoidal curve because in this curve we can easily identify the equivalence point, which is the point shown having the steepest slope or the greatest change per volume of titrant. So the sigmoidal curve plots the P function of the analyte or titrant in the y-axis versus the volume of the titrant in the x-axis. So here's the x-axis with the volume of titrant added, and the y-axis with the P function of the analyte or titrant plotted. The equivalence point corresponds to the volume of the steepest change in the P function. So that would be here. It is convenient and fast to use for general titrations. On the other hand, linear segment curves plot the instrument response in the y-axis and the titrant volume in the x-axis. So this is usually used when we have an instrument reading. So the equivalence point would be the intersection between the two linear segments. That would be this linear segment and this linear segment. So the intersection would fall somewhere here where the two linear segments intersect. It is useful when the reactions involved are complete and when the excess reagent or analyte is involved, or when an excess reagent is added into the system. This time we will focus on neutralization titrations, specifically for strong acid, strong base titrations. There are several steps or stages in the titration that would be before the addition of the titrant, meaning that we only have the analyte in the system, before the equivalence point, at equivalence point, and beyond the equivalence point. So before the addition of the titrant, the flask only contains the analyte. And the analyte is solely responsible for the pH of the system. So at this point, the reaction has not started yet. The flask simply contains the analyte, of course, the indicator of choice. But in this case, if we're going to use phenolphthalein, then the mixture should be colorless. Next, before the equivalence point. This is when some titrant is already added into the flask. Some of the analyte already reacted with the titrant. So in this case, the volume of the titrant here should already decrease. We should already have a reading. However, there is no noticeable change in the flask because the endpoint has not been reached yet. And the flask contains the salt, which would be the product of the acid analyte contained in the flask reacting with some amount of the basic titrant, and then we still have excess analyte in the system. At equivalence point, this is when the amount of hydroxide ion completely neutralizes the hydronium ion in solution. So at this point, there is no excess analyte, there is also no excess titrant, and instead they are completely equivalent with each other. And if we are using a phenolphthalein indicator, we should already be able to see a faint pink color. So the pH at the equivalence point for a strong acid, strong base titration is always 7. That is because all of the acidic species here has completely reacted with the basic species coming from the titrant, and they have all been completely converted into a neutral salt. After this, beyond the equivalence point, it will be visually manifested by a strong pink color coming from the chemical indicator if you're using phenolphthalein. And then all the analyte is consumed completely, converted into salt, and aside from that, we're going to have an excess amount of titrant in the solution. So in this case, the excess titrant will dictate the pH of the solution. So let's have an example. Generate the hypothetical titration curve for the titration of 50 ml of 0.05 molar hydrochloric acid with 0.1 molar of sodium hydroxide at 25 degrees Celsius. So we are given the neutralization process wherein sodium hydroxide plus hydrochloric acid gives sodium chloride, which is aqueous in the system. So it will dissolve into sodium ions and chloride ions plus water. Therefore, the net ionic equation is simply the hydronium ion, or H+, plus the hydroxide ion forming water. So before the addition of the titrant, only hydrochloric acid is in the flask, and we do not see any color change yet. So the pH is determined by getting the negative log of the hydronium ion concentration, which is simply given in the problem. So that's negative log of 0.05 molar, and we compute the pH to be 1.30 we are supposed to report it in 3 significant figures. However, most pH meters are only able to report up to 2 decimal places of the pH. Therefore, the final answer is 1.30. Again, in terms of significant figures, we are supposed to report it in 3 decimal places. However, in all practical purposes, pH meters usually report only until 2 decimal places. So that is why, in this case, we can expect the pH to be just 1.30. Next, after the addition of 10 ml of 0.1 molar sodium hydroxide, we would have to determine the point in titration, which point in titration the system already is. So to do that, first we understand that the reaction between HCl and NaOH occur in a 1:1 ratio. Therefore, to determine the concentration of HCl in the system, that would be starting from the millimoles of original HCl present in the system, we subtract the number of millimoles of sodium hydroxide added. So this is only possible because the reaction occurs in a 1:1 ratio all over the total volume of the solution. So substituting, we can get the millimoles of original hydrochloric acid present in the analyte by multiplying the volume of HCl with the concentration of HCl expressed in millimoles per ml. So we cancel the ml here. We will be left with millimoles HCl. And then here, to get the number of millimoles of HCl consumed by NaOH, that would be 10 ml NaOH multiplied by the concentration of NaOH, also expressed in millimoles per ml, so that ml can be canceled out. And then we convert the number of millimoles of NaOH into the number of millimoles HCl. So this will cancel out and we will be left with millimoles HCl. So we can subtract this term and this term. Again, this term would represent the number of millimoles of HCl originally in the solution minus the number of millimoles HCl that has been consumed by sodium hydroxide titrant and converted into salt, which does not contribute to the pH of the system. All over the total volume of the solution, so we had 50 ml of the analyte plus 10 ml of the titrant. This gives us the new molar concentration of HCl in the system. So doing the calculations, we get the HCl concentration to be 2.5 times 10 raised to the negative 2 molar. That is equivalent to the hydronium ion concentration because HCl is a strong acid. Therefore, it dissociates completely into H3O plus and chloride ions. And then using this concentration for the hydronium ion, we can solve for pH by getting the negative log of that concentration and report the final answer to be 1.60. So that is the final answer. This is the pH after the addition of 10.0 ml of 0.1 molar sodium hydroxide. Next, at equivalence point. At this time, the volume of the titrant is not given at all. We were just told that the system is already at equivalence point. Nevertheless, even though we do not know or we were not given the volume of the titrant here, at equivalence point, we know that the HCl analyte would have been completely converted into salt and water. Therefore, Kw, or the ion equilibrium constant for water, predominates in the mixture, and that is equivalent to 1 times 10 to the negative 14, getting the square root of that because that is equal to the product of the hydronium ion concentration and the hydroxide ion concentration. That would give us 1 times 10 to the negative 7. Or you can just skip these steps if you have already memorized or if you're already familiar with the fact that pure water would have 1 times 10 to the negative 7 molar of hydronium ions and hydroxide ions. So therefore, the pH is the negative log of the hydronium ion concentration, or simply 7.00. Again, reported in 2 decimal places because practically all or most pH meters only report up to 2 decimal places. And again, looking at the illustration, if we are having phenolphthalein, then the endpoint should be a pale pink color. Next, after the addition of 25.10 ml of 0.1 molar sodium hydroxide, so the species left on the mixture would be excess sodium hydroxide. How do we know how much sodium hydroxide is in excess? That would be from the number of millimoles of sodium hydroxide we have added in total, minus the number of moles of sodium hydroxide that is needed to completely react with the hydrochloric acid present in the system. So again, the sodium hydroxide concentration would be equal to the number of moles of sodium hydroxide in total added to the system minus the number of moles of sodium hydroxide needed to completely react with the hydrochloric acid analyte all over the total volume of the system. So here, we start with the volume of the titrant multiplied by the molarity of the sodium hydroxide titrant, and we cancel MlNaOH, And then here we start with the volume of the acid times the concentration of the acid times the mole ratio of the acid and the base, so that we're able to convert this whole term into millimoles NaOH. And then we cancel all units as applicable, and we will be left with millimoles NaOH minus millimoles NaOH all over the total volume, which is 50 ml, coming from the HCl analyte, plus 25.1 ml, which is the volume of the titrant. So after doing all of the calculations, we get the sodium hydroxide concentration, which is 1.33 times 10 to the negative 4 molar. And because this is a strong base, we assume that, well, we don't assume because we know for a fact that this is going to dissolve completely, giving the same concentration of the hydroxide ion. Getting the negative log of that would give us POH, so 3.88. Subtracting this from 14, we would be able to get pH. So the pH of the solution or the system at this point would be 10.12. Okay, now we have computed for 4 points in the titration process of that system. So starting from 0, 10 ml titrant, at equivalence point, which is 25 ml titrant, and after equivalence point, which is 25.10 ml titrant. So plotting that and also adding extra points in the curve, we would have this graph or this titration curve. So here are the points that we have computed for with their corresponding pH levels. So notice that the titration curve starts at the bottom since the starting pH of the analyte is acidic. So we had hydrochloric acid, therefore we started with an acidic pH. And then an addition of 10 ml only gave us a minute increase in pH. So as the basic titrant is added, the pH of the system increases gradually. However, notice that as we are nearing the equivalence point, the pH change is becoming more and more steep. So until a small volume of titrant causes a drastic pH change. And that is where the equivalence point is found. So the titrant at this point should be added dropwise to avoid over-titration. Okay, so this is how these points are plotted in the titration curve. Okay, so before I proceed to the applications of titrametric methods, there's just one point I would like to make. Normally, titrations are done because we would like to know the concentration of the analyte. Notice, however, in this case that we already know the concentration of the hydrochloric acid analyte. So what's the point of calling it an analyte if we know already its concentration? So for that problem, we were already given the initial concentration of the analyte for the purpose of being able to plot the titration curve. So in this lesson, we are studying the titration curve. We are concerned of the behavior of the pH during different stages of the titration. Okay, but again, if we're going to do this in the lab, in most cases, we are more concerned with the pH of the analyte or with the initial concentration of the analyte. This is just an exception because we are studying titration curves and therefore more focused on the behavior of the pH at different stages of the titration. That is why we were already given an idea of the concentration of the analyte at the start of the titration. So moving on to the applications of titrametric methods. So here are some of the applications of titrametric methods. First, elemental analysis. That's when we analyze or calculate or determine the concentration or amount of an element in a sample. Nitrogen determination using the Keldal method. Obviously, that's an measuring the nitrogen present in a sample. Sulfur determination, determination of ammonium salts, nitrates and nitrites. So for nitrates and nitrites, we are supposed to perform this for water analysis, water quality analysis. Then we have carbonate and carbonate mixtures analysis, determination of organic functional groups, determination of salts, water hardness determination, metal ion analysis, water determination using the Carl Fisher agent, iodine titrations. So we will be having some lab activities on this. So during the online implementation of the lesson, we will just have alternative lab activities. So for the navigate part, you're asked to calculate the pH during the titration of 50 ml of 0.05 molar sodium hydroxide with 0.1 molar hydrochloric acid at 25 degrees Celsius after the addition of the following volumes of reagent. So here we are given different volumes of the reagent. So you simply have to do the same process as what was described before. So letter A, that would correspond to before the addition of any titrant. That would mean that the pH is dependent on the analyte. Letter B, for letters B, C, D, E. Okay, so here we actually do not know yet if this is before equivalence point or at equivalence point or after equivalence point. So what you would have to do is first to assume that this is before equivalence point. Therefore, you'd have to get the number of moles of you'd have to get the number of moles of NaOH that remains unreacted with HCl. So in that case, if you find that there's still NaOH present in the system, then that would be before equivalence point. Now, if you try to do the subtraction of the number of moles NaOH minus the number of moles of HCl that has consumed it, and you get 0, then that means it's already at equivalence point. And if you get 0, you can simply drop all of the calculations and say that the pH of the system is 7. Now, if you find that there is an excess HCl already, then that would mean that the system is already beyond the equivalence point, and that the pH would solely be dependent on the excess HCl. Also notice that for this problem, we started with sodium hydroxide as the analyte and HCl as the titrant, meaning instead of the titration curve, which I have shown you that it starts from a low pH going to a high pH. So this time, we're going to have a pH curve that looks something like this, where you start with a very high pH and then which gradually decreases until you reach equivalence point, and then after equivalence point, you'll also have a very acidic solution. because the pH now will be dictated by the excess HCl in the system. So you'll also be asked to generate the titration curve for that given system. You will be able to generate pH versus a pH versus volume of acid or volume titrant curve, which should look like this, but please make sure that your graphs are labeled and the points are plotted properly. Okay, and also one final point that I would like to make is that when you're computing for the concentrations before equivalence point, remember that the concentrations that you will get are hydroxide ion concentrations. Therefore, getting the negative logarithm of that would give you POH and not yet pH. So remember that what you're getting somewhere here would be the concentration of the hydroxide ions. Getting the negative log of that would give you POH. You'd still have to subtract from 14 to give you pH. On the other hand, after equivalence point, that would be found somewhere here. So the concentrations of HCl would immediately give you the concentration of the hydronium ions. Therefore, getting the negative logarithm of that immediately gives you pH. Okay, and to note, you're asked to choose 5 of the listed applications of titrametric methods. Write the reactions involved for each and list the titrants, analytes, and indicators used in the analysis. That ends lesson 1.12. Thank you for listening. I hope this video has helped you again understand lesson 1.12. Bye, class.